All right, welcome everyone. In this lesson, we're going to talk about the idea of differentiability. So specifically, what we're going to be doing is by the end of this lesson, you're going to be able to determine where a function is differentiable, either given the graph of the function or a formula for the function, and then be able to explain why the function is either differentiable there or why it's not differentiable there. All right, so let's get started with some definitions. First of all, what do we mean by differentiable? So we say a function f is differentiable at location x provided this limit exists. The limit is h goes to 0 of f of x plus h minus f of x all over h. And we've seen this limit before. This is a special limit, and if this limit exists, we give it a special name. We call this the derivative of f at location x, f prime of x. All right, so we say a function f is differentiable at location x if this limit exists. If this limit does not exist, well then we say our function is non-differentiable at location x. Okay. So we've seen this limit calculation before. And going forward, it's important to keep in mind that f prime here is just a brand new function. So we start with some original function f, and we go through this limit calculation, and what we end up with is, in a lot of cases, is a brand new function which we call f prime. So f prime is a brand new function that's derived from our original function f. And so it's a function, so it makes sense to ask questions like, well, what variable are we going to use? Or what is the domain of this derivative? And the answer to these is it inherits a lot from the original function. So for instance, the variable, well, if our original function f is using variable x, well then f prime is also going to be using variable x. Same thing for the domain. The domain of f prime is going to be equal to all the x values that were in the domain of f. Not quite there. We have one exception, and that's where this above limit exists. So the domain of f prime is going to be equal to the domain of f, but we have to go through and throw out all of the x locations where this limit did not exist. So conceivably, the domain of f prime may be smaller than domain f. So to find the domain of f prime, we start with the domain of our original function, and then we throw out all of those x locations where this limit didn't work. So at best, the domain of f prime is going to equal the domain of f. But a lot of times what happens is there's some x values there which we have to throw out. So the domain of f prime might shrink a little bit. All right, let's look at an example. Example 1, we're going to state the domain for function f and its derivative f prime. And here function f is the square root of x. So we've actually looked at this function in the last lesson, and we actually calculated its derivative. So f prime is 1 over 2 times square root x. So we actually went through and calculated this. What is the domain of f here? Well, we know that for square root functions, we can plug in all positive numbers, and we can actually plug in 0 here. So it's the closed interval from 0 to infinity, where we use this closed bracket to indicate we want to include 0. Square root of 0 is perfectly fine to plug in to our square root function. What about domain f prime? What's the domain of f prime? Well, at best, it would be this interval, but we see that 0 isn't going to work because plugging 0 into this would give us division by 0, which is undefined. And actually, if you were to go through and try to use the limit definition to calculate the derivative at x equals 0, you would run into issues. You would run in precisely what we're seeing. You'd run into kind of a division by 0 situation. So the domain of f prime, we actually have to throw 0 out. So it's the open interval from 0 to infinity, and we use a parenthesis here to indicate that we're excluding 0. We don't want that in our interval. So here's the domain of f prime. So we see something's happening at x equals 0, and we say f is non-differentiable at x equals 0. Now, why is that? Well, we get division by 0, but if we look at the graph of f prime, so here we have the graph of just our square root function, and here we have the graph of the derivative, so 1 over 2 times the square root of x. And something is interesting is happening near x equals 0. So let's take a look. And let's start with the limit of f prime as x approaches 0 from the right. What is the limit of f prime as we approach 0 from the right? And you can see from the graph here, it's an infinite limit. It's getting larger and larger positive. The graph of f prime is going up and up and up the closer we get to 0. And so what we have here is f prime has a vertical asymptote at x equals 0. Now, what's going on with our original function? So this is why f prime doesn't work out at 0 here. But let's see what's happening to our original function. What's kind of the corresponding behavior? So f prime has a vertical asymptote at x equals 0. And to really see the behavior here, we want to zoom in on our function f right at x equals 0. So let's zoom in right at that point x equals 0 on our graph of f. And when we do that, let's get really close. And let me get rid of the point there. So here's our point. And what we see is really close to x equals 0, our function, it looks like a vertical line. It looks like it's behaving, straight up and down. It looks like it's behaving like a vertical line. And this isn't coincidence. What we have here is our function f has a vertical tangent at x equals 0. So it looks like, just as we saw, if we were to zoom in on that point, our function looks like it's straight up and down near x equals 0. So our function has a vertical tangent line near x equals 0, or at x equals 0. And then corresponding, f prime then has a vertical asymptote at x equals 0. So we can see this is an example for what might happen if our function is non-differentiable. We might have this case where we have a vertical tangent line. Now we are going to see there's other cases of this. And so it's going to be helpful to kind of first make a definition. How do we define the slope of the curve at a point? And so the way we define, let's look at our graph here. Here we have a curve, a nice parabola. And we have this point on our curve that we're interested in, point P. And we want to define the slope of our curve at that point. Well, how would we do it? Well, we would draw in our tangent line. And we know our tangent line has a specific slope. So then we say that the curve, our curve at point P, has slope equal to the slope of the tangent line. So the slope of our curve at point P is equal to the slope of our tangent line at point P. And this makes sense. If we were to zoom in, let's zoom in on point P. Here it is. You can see the curve and you can see the tangent line, but right around point P, you can't really tell the difference. Our curve looks really similar to our tangent line right at that point P. And you can tell at that point, it looks like our curve and our tangent line are going in the same direction. And so this is a perfectly natural way to define the slope of our curve. It's just the slope of our tangent line. And so here's an example of a point where it's differentiable. And we're seeing what's happening here is that the curve and the tangent line are just going in the same direction. They look very similar to each other. So kind of what does it mean then for a function, kind of graphically, what does it graphically mean for our function to be differentiable? Well, a function is differentiable provided its graph does not have any abrupt changes or vertical tangents. So we've kind of seen an example of what it looks like when we have a vertical tangent, but what about when we have an abrupt change? What do we mean by abrupt change? And there's kind of two scenarios here. Our function f has a jump or a break or a hole. At a specific x value. So an abrupt change is where our function has a jump, a break, or a hole. Another possibility is where our function has a very sudden change in the slope. So if there's a very sudden change, a very drastic change in the slope of our curve, well then we might have a place there where it's non-differentiable. And another way to think of it is for a differentiable function, zooming in on a point, the curve should look like a line. And that's kind of what we're seeing here. So this function is differentiable at x equals 1 because when we zoom in on that point, it looks like a line. So another way to think of this in terms of tangent lines is our function can't have any abrupt changes, it can't have any vertical tangents, and if we were to zoom in on a point on the curve, it should look like just a line. So we say our function f is, another way to think of it kind of graphically is our function is differentiable at a point provided the curve looks like a line near that point, except a vertical line. Vertical line, there's an issue. But if it looks like kind of like a diagonal line like this or a horizontal line, perfectly fine. So let's keep this in mind. We can kind of think of it two ways. We could think of our function f is differentiable if its graph looks like a diagonal line or horizontal line. Or if we're thinking of it in terms of slope, there's an abrupt change in our slope or we have a vertical tangent. So let's see some examples here. So in the next few graphs, we're going to see examples of functions that are non-differentiable at x equals 2. And in these first two, let's start with this one. What we're seeing is in this one, there's a sudden change in the slope. So we call this a cusp or a corner. And, there's a few ways to kind of convince yourself that this is non-differentiable. If you were to zoom in on this point, it doesn't look like a line. So there's this kind of a corner to our graph here. There's this cusp. So differentiable functions should kind of have rounded edges. Another way to think of it to some extent. If we were to think of it in terms of slope, though, if we were to look on the left side here, if we were to look right in here, let's see, I want to if we were to look on this left side, what's happening here is the slope of our curve is positive. And actually, as we move closer and closer to 2, the graph is actually getting steeper. So what's happening on the left side here is we have a large positive slope. Our curve has a large positive slope. And if we were to look on the other side, what's happening on the other side over here is that over here now it's going down. So it's a large negative slope, and it's fairly steep. So over here it's a large negative slope. And it's not a subtle transition either. So it's this sharp, drastic change. We go from having a large positive slope on one side to a large negative slope on the other side. So there's this fairly sudden change in the slope of our graph. So we're getting this cusp, or we might call it a corner. There's this sharp edge here, essentially. So zooming in on this point, this thing doesn't look like a line right at this point P, or at this point at x equals 2. So there's a few ways to kind of convince yourself that this thing is not differentiable. All right, what about this graph? Well, here we've kind of seen this before. This one has a vertical tangent. This one has a vertical tangent line at x equals 2. So if you were to try to draw the tangent line, it looks like, right at x equals 2, it looks like a vertical line. And you zoom in, kind of what we've seen before, zooming in at x equals 2, right at x equals 2, it looks like a vertical line there. So that's another case where our function is non-differentiable, is when we have this vertical tangent line. And what happens at vertical tangent lines is our function it's very sensitive to small changes. So if I were to make a small change in my input here, so say I were, instead of looking at 2, I were to look at 2.01, a small change in the input is going to give a comparatively large change in the output of the function. So whenever we have a vertical tangent, our function displays some sort of sensitivity to small changes. So just another example of what it means to be non-differentiable, though. So if we have this, if our graph kind of looks like a vertical line, we know vertical lines don't mix well with functions. So there's kind of this hesitation here. There's this sensitivity in our function where small changes in our input produce large changes in our output. So if we have a vertical tangent, though, our function is non-differentiable there. So what these two examples show, though, these graphs are non-differentiable. So these are both non-differentiable at x equals 2. But they are both continuous at x equals 2. So we've looked at this idea of continuity before, and graphically the way to think of it is we can just trace over this curve without ever taking our pen off the page. And we see that we can do that in each of these. So both of these graphs are continuous, and specifically they're continuous at x equals 2. Let's look at a few more. Now here, these three graphs, these are functions that are non-differentiable at x equals 2. So these are all non-differentiable at x equals 2. And in each of these, they're discontinuous at x equals 2 as well. So all three of these graphs are both non-differentiable at x equals 2 and discontinuous at x equals 2. And you can kind of see in this first one we have a hole. This one we have a kind of a jump discontinuity. We have a jump in our graph. And then this one we have like an infinite jump. And so, why are they discontinuous? Well, imagine trying to trace over these. In this first one, we're okay on this first bit here, but then eventually we get close and we have to take our pen off the page, bring it back down, draw this dot, take it off again, bring it back down, and then we can continue on. So it's discontinuous at x equals 2. What about for the jump? Same thing, we start, this is okay. Then we get around here, we have to take our pen off the page, bring it back down, draw this dot, and then keep going. And then same thing with this infinite jump discontinuity. We can draw on the left side, and we can keep going up and up and up, but eventually we have to take our pen off the page, bring it, and then continue on the right side. So each 3 of these graphs here are discontinuous at x equals 2. And so, what does it mean to be differentiable? It means we have to be able to draw the tangent line. So the question is, how would you draw a tangent line at x equals 2 here? It doesn't really make any sense in all 3 of these. So how would you draw a tangent line at x equals 2? Well, how can you draw a tangent line to just a point? There's no other curve here. And then if we were going to draw a tangent line here, how come this point's missing? So how would we be able to draw the tangent line there? So there's a lot of ambiguity in how we would actually draw the tangent line at x equals 2 here. Same thing here. If we wanted to draw the tangent line at x equals 2, well, if we were kind of using points from this side, we might want to draw a tangent line that looks something like that. But if we were using points from this side, we might want to draw a tangent line that's down here. So the question is, which line should we be using? And it's not clear. And so the limit doesn't exist. That limit as h goes to 0 doesn't exist for all 3 of these functions. Same thing for x equals 2 here. I mean, with an infinite jump, our function isn't even defined here. And if we were to use points from the left side, we'd have a large positive slope for our tangent line. And if we were to use points from the right side, it'd have a large negative. So there's this really a sudden change in the behavior of the slope of our curve going from the left side of x equals 2 to the right side. So again, that limit doesn't exist. It's non-differentiable. All right. So just some examples of where our functions graphs might have a non-differentiability, point of non-differentiability. Let's look at example 2. Let's do some calculations. We're going to determine whether this function is differentiable at x equals 20 or whether it's non-differentiable at x equals 20, and it's a piecewise function. And we're interested at x equals 20, and we see that this piecewise function kind of breaks into pieces at x equals 20. So we want to see what's going on here. And so in order to figure out whether a function is differentiable at a specific x value like this, what that means is we need to calculate that limit, our derivative limit. The limit is h goes to 0 of c of 20 plus h minus c of 20 all over h. We need to calculate this limit. If this limit exists, then yeah, our function's differentiable there. If this limit does not exist, well then it's non-differentiable. All right, so as h goes to 20, or h goes to 0, we know we have this 20 plus h that we're plugging in, and we know that our function kind of splits up right at x equals 20. So there's this kind of breaks into pieces there. So in order to calculate this limit, the limit as h goes to 0 kind of overall, we have to look at the left and the right side limits. So we have to do the limit as h goes to 0 from the right and the limit as h goes to 0 from the left. So let's start with h going to 0 from the right. And we're going to calculate this. And we're going to have to calculate c of 20. So let's just actually do that first. So let's plug 20 into our function. And it's a piecewise function, so we have to identify which piece to use. We find x equals 20 right here in this top piece. So we're going to use this formula to calculate, to plug into. So let's actually do that. C of 20 is equal to 100 plus 12 times 20, which is, this is 240, so we get 340. Okay. What about this C of 20 plus h? So h is approaching 0 from the right, and so if h is approaching 0 from the right, that means that h is close to 0 but slightly bigger. So we're trying to figure out which piece of our function to use for this 20 plus h. So we know with a piecewise function we have to identify which piece to use. So that's what we're trying to do here. So we're trying to figure out, is this input 20 plus h, is it bigger than 20 or is it less than 20? That'll tell us which piece to use. So 20 plus h is a small positive number, so that means 20 plus h is slightly bigger than 20. So we need to use this piece right here, this 180 plus 8x, when we evaluate. So let's actually fill that in. So we're going to plug 20 plus h into that second piece. So I go to my second piece here, 180 plus 8x, and I'm just going to change this x to a 20 plus h. So I'm just plugging in. All right, so that's what I get when I evaluate my function c at 20 plus h. And then let's use what we get when we plug 20 in, and we're going to subtract, and we know what we got there was 340. Okay, let's simplify this down a little bit. So we have 180 plus 160 minus 340. So that ends up being 0. And then we end up with 8 times h all over h. So, distribute the 8 here, so we get 160. 160 plus 180 is 340. And then we have a minus 340, which cancels that off. And then we have this 8 times h, and that's all that we have left. Now if we cancel this, the h's cancel, we get the limit of 8. And that's something, it's just the limit of a constant, so we can do that. It's 8. All right, so the kind of the limit as h goes to 0 from the right is equal to 8. Now we need to check, well, what's the left side limit? What's the limit as h goes to 0 from the left? And let's do that calculation. So now it's the same limit. The limit as h approaches 0 of c of 20 plus h minus c of 20 all over h. But now we're using h values that are slightly smaller than 0. So it's the limit as h approaches 0 from the right. So again, we know we've already evaluated 20 into this function c. We want to evaluate 20 plus h because now we're using different h values. So in this left side limit, h is close to 0, but it's slightly smaller. So that means when we add 20, we get that 20 plus h is going to be smaller than 20. So h is slightly negative here. Our input h here is slightly negative, which means 20 plus h is going to be slightly smaller than 20. So when we actually go to evaluate this, we're trying to decide which piece to use when I plug 20 plus h in. And 20 plus h is slightly smaller than 20 because h is slightly negative. So I go back to my piecewise function and I look for where the piece that tells me what to do when I have inputs that are slightly smaller when they're smaller than 20. And so here we see x is less than 20. I need to use this top piece. So when I plug in, I'm going to have the limit as h goes to 0 from the left. And when I plug 20 plus h in, since h is slightly negative, my inputs are slightly smaller than 20, I need to use that top piece here because that tells me what to do when my inputs are smaller than 20. So I'm going to plug 100 plus 12. I'm going to use that piece. So I'm going to get 100 plus 12, and then instead of x, I'm going to plug in 20 plus h. And then the x equals 20 plugged into this function c, that we've already done that. We found it was 340, and then I'm subtracting, and all this is going to be over h. Let's simplify this. So I end up with 100 plus 240, or plus 240. So 100 plus 240 is 340, and then I'm subtracting 340, so those are going to cancel. And what I'm left with then, when I distribute the 12, I'm going to be left with 12h over h. As h approaches 0 from the left, the h's cancel, and I'm left with then just the limit of 12 as h approaches 0 from the left, which is just 12. So what we've done is with this left side limit, we've shown that this derivative type calculation here that we're trying to do gives us a result of 12. But if we go to the right side limit for this derivative type calculation, what we're seeing is that the limit is 8. And so because the left and the right side limits are not the same, this overall limit, the limit as h approaches 0, this is the derivative that we would be trying to do. The derivative here does not exist. So since the left-hand limit and the right-hand limit are not equal, this means the limit as h goes to 0 of c of 20 plus h minus c of 20 all over h does not exist. So since the left hand and the right hand limits we found were 12 and 8, since they're not equal, our overall limit does not exist. And because this overall limit does not exist, this is our derivative type calculation that we would want. It means our function here is non-differentiable at x equals 20. So since that limit did not exist, we did the left and right hand limits separately, found they weren't equal. That limit did not exist, which means our function is non-differentiable at x equals 20. And if we look at the graph, you can kind of see it might be slight, but if we were to, there we go. If we were to zoom in at x equals 20 there, there's a kind of a sudden change in the slope. Now it's not as sudden as some of the other examples that we've looked at, but there's a slight corner here. It's not a gradual change. It's not a rounded edge here. It's a slight corner. And so really what we're seeing is that there's this, what we calculated by doing, say, the left-hand limit as h goes to 0 from the left. What we just calculated is on this side, it looks like this line. It looks like on each of these pieces, our function looks like kind of like lines, but where they come together, there's an issue. So on this side, what we calculated is that the slope was 12. And then on the right side, we calculated that the slope was 8. And it didn't gradually transition from 12 to 8. It was just this sudden change. We're going from having a slope of 12, and then all of a sudden we have a slope of 8. So there's a sudden change in the slope, or an abrupt change in the slope at x equals 20. On the left side, our slope is 12. On the right side, our slope is 8. And we don't gradually go. So we don't go down to 11, then 10, then 9, then 9.5, then 9.1, then 9, or 8.1, 8.01. There's no gradual change where we gradually go from having a slope of 12 down to a slope of 8. We just go, here's a slope of 12, and then all of a sudden we're down to a slope of 8. There's just a sudden change in the slope of our curve. So that's what do we mean by having a non-differentiable point. All right. So as we've seen in some of our examples and some of the graphs we've looked at, there's a relationship between a function being differentiable and being continuous. And here is a result that tells us explicitly what that relationship is. It says, if function f is differentiable at location x equals a, well then the function f is also continuous at location x equals a. So if we know our function f is differentiable at a point, well then f is also continuous at that point. So this is pretty remarkable. It really tells us that if we can calculate the derivative of a function, then the graph of that function doesn't have any jumps or breaks or holes in it. So if we can calculate the derivative on an interval, then on that interval, there's no jumps or breaks or holes. So our function's continuous then on that same interval. Now this theorem, this result, doesn't tell us everything. So what it does tell us, though, is that every differentiable function is continuous. So again, if you can calculate the derivative on an interval, then you're guaranteed that on that interval, on that same interval, there's not going to be any jumps or breaks, no funny business. There's no holes in the graph. And it kind of works in reverse in some way. So if you know your function is discontinuous at a location, if you know your function does have a jump or does have a break in the graph, well then that function is automatically non-differentiable at that location. So this theorem, if you read it one way, says every differentiable function is continuous. If you read it kind of what we call the contrapositive, what it says is that if this doesn't work, then this doesn't work. So if f is discontinuous, then f is non-differentiable. So just a warning here, though. If f is continuous, then we don't know what f is doing in terms of being able to calculate the derivative. So differentiable is a stronger statement. If we know our function's differentiable, it guarantees continuity. Continuity is kind of weaker. So if we know our function is continuous at a location, it doesn't really tell us what function f is doing at that location in terms of differentiable. It may or may not be differentiable. So if f is continuous at a location x equals a, it doesn't really say what f is doing in terms of differentiability. May or may not be differentiable there. And so we've seen examples where our function's continuous at a location, but it's non-differentiable. And then we've also seen examples where it is continuous and it is differentiable. So let's take a look. So here in these two graphs here, each of these graphs were continuous at x equals 2, but they were non-differentiable. So it's not enough to say if you know your function's continuous, it's automatically differentiable. It might not be. So continuity does not imply differentiability. So knowing that a function's continuous, it's really not enough to tell you anything about the actual differentiability of the function. But if you know your function's differentiable, this is much stronger. You would know then the function is continuous there as well. Okay. Just try one more example. Example 3, we're going to determine whether this function is continuous and whether it's differentiable at x equals 15. And it's a piecewise function. And we see that, there's different pieces here, 20 plus 2x, 400 plus 2x, 600 plus 2x. And then we have these different pieces. So x between 0 and 15, x between 15 and 30, and then x between 30 and 45. We're interested for this example for x equal to 15. And we see that 15 is kind of one of the places where our pieces split up, where we break up our piecewise function here. So we know with piecewise functions, a lot of times continuity becomes an issue where those pieces come together. So let's start by checking continuity. Is this function continuous at x equals 15? So a lot of times with these piecewise functions, the pieces don't quite line up. There's normally there's possibly a jump or a break in the graph. All right, so to check continuity, what do we need? We need to do the left-hand limit of our function as x approaches 15. We need to do the right-hand limit of our function as x approaches 15 from the right. And then we also need to plug 15 into our function. And for continuity, we need all three of these values to be equal. So if the left and right-hand limits are equal, then the overall limit's equal. And we need all three of these values to be equal in order to get continuity. So the left side, the right side, and then what's happening directly at x equals 15. All right, so the question is, this is what we're trying to do. Is this the case for this function? This is what we want to show. All right, so let's start with the left side limit here. Let's do the limit of c of x as x approaches 15 from the left. So the question is, well, x is approaching 15 from the left. Which piece should we use? Should we use this piece or this piece? And if we're approaching from the left, that means we're using values that are slightly smaller than 15. So we're close to 15, but take away a little bit, subtract a little bit. So here, x is slightly smaller than 15. So that puts us in this first piece. So we're going to use 200 plus 2x. This is just a polynomial, so we can do direct evaluation. So just plug 15 into this to calculate the limit. We get 200 plus 2 times 15. 2 times 15 is 30. We end up with 230. Again, direct evaluation here, because 200 plus 2x is a polynomial. Okay. Now, what about the right side limit? Let's do the right side limit. As x approaches 15 from the right. Now, if this is the case, x is getting closer and closer to 15, but we're using values that are slightly bigger. So x is going to be slightly bigger than 15. And so in order to calculate this limit, we need to use values of x that are slightly bigger. We need to use that second piece, 400 plus 2x. So let's fill that in. We're going to do the limit of 400 plus 2x as x approaches 15 from the right. Now this is also a polynomial, so we can just calculate this limit with direct evaluation. And when we do that, we get 400 plus 2 times 15, which is 430. So these two values are not the same, which automatically tells us this function is not continuous. The left side and the right side aren't kind of meeting up at the same place. So together, the fact that these limits are different, since the left-hand limit does not equal the right-hand limit, this means the limit of c of x in general as x approaches 15 does not exist. So the left hand and the right hand limits are different for our function c of x, which means that the overall limit does not exist. And if that overall limit does not exist, then our function is not continuous. So this means our function is discontinuous at x equals 15. So from that previous result, if we know our function is discontinuous, well then it's non-differentiable as well. So our function here is discontinuous, like we said, because the overall limit did not exist at x equals 15. And so that automatically means then that it's non-differentiable at x equals 15. So, we could try it. If you really wanted to, you could go through and do something similar to what we did in example 2, where we actually try to calculate our this derivative limit. So you'd break it up, do the right side, do the left side. But what you would find is that this limit didn't exist either. So we're kind of getting that with our continuity. The left side and the right side are not doing the same thing. They're not matching up. Something similar would happen if you tried to do that derivative limit. You'd see the left side and the right side for that derivative limit wouldn't match up either. All right, so kind of different ways here to check whether a function is non-differentiable or not. So we could check it directly using, like we did in example 2 here, right from the definition. We could possibly show in example 3 that our function is discontinuous. And these are cases where we actually have a formula. Or as we saw earlier, there's graphical scenarios. So by looking at the graph, you might be able to pick out a corner or a cusp or a vertical tangent line, or where there's just a jump or a break in the graph. So that's really the idea, is given a formula, given the graph of a function, can you identify where the function is differentiable and where it's non-differentiable? All right, so that's going to do it. And we're going to keep developing this intuitive idea of this conceptual idea of differentiation in the next lesson. So we're going to work more with this idea of calculating derivatives from this limit definition. We're just going to look at a few more applications. So we'll see you then. Bye-bye.